Determine the area which is enclosed by the x-axis and the curve given by this little quartic here. Y equals x squared minus 1 times 4 minus x squared. So trying to visualize this, we got the x-axis, which if you wanted it, it is a curve. It is y equals 0. But they'd be a little coy with that. So x-axis and this curve here. Okay, and we're talking about the area enclosed. So it's not, it might at first glance look like, oh, we just want the area under this thing. No, because what this curve does, it's downward facing. So it's going to look roughly like this. Something like this. What we're after with this question is these little areas. Okay? The areas that on one side have the x-axis, but we don't care about top or bottom, and one side have this little quartic curve here. So it's these, rather than trying to figure out this endpoint and this endpoint and doing an integral here. No, we want every bit of area to count. Okay, so we want all of this to be treated as positive, and that means that we're going to have to be careful. But yeah, the curve here twists around the x-axis. We will be able to see. So here's a quick sketch, but we'll also do this sort of algebraically, in case that's sort of who we are. So the first thing we're going to do is we're going to take a look at points of intersection. Okay, we need the points of intersection anyway, even if we didn't know that there were twists, because you'll notice the question didn't give me bounds. Find the area under this curve over what bounds? Well, you didn't give any, so at least the points of intersection might be the two endpoints of my definite integral. Okay. So the x-axis, as I say, is really just y equals 0. And the other curve was y equals x squared minus 1 times 4 minus x squared. So how do you find points of intersection? You set the expressions for x equal. Now you might say, hold on, this doesn't have any expressions for x. Yes, it does. It's just a boring x, doesn't matter what x is, the output of my function is 0. But that is the formula. So the formula involving x, it just doesn't have any x's. And someone was nice enough to give me this, this polynomial here already factored. We will have to expand it out when we go to do the integration, but we're not completely done factoring. This is difference of squares. And we can see pretty quickly that we're going to have 4 points of intersection. X can be 1, minus 1, 2, or minus 2. And as you saw when I did my little sketch, that absolutely is what happened. But I'm not going to rely on the graph here. Okay? But, okay, so our area is going from minus 2 all the way up to 2, but as it will turn out, the curves are twisting at 1 and minus 1. Now, if you're not good at drawing graphs, you don't know that, but anytime you have more than 2 points of intersection, there's a possibility that the curves might twist around each other. In this case, yes, they do, but I'm going to do this question pretending I don't know how to graph, just to show you that it can all be done algebraically. So it's possible that there are twists. Okay? So what do? You don't set up the integral just from minus 2 to 2, because we want those areas individually. We don't want anything to cancel each other out. So what we're going to do, we're going to set up the area from minus 2 to minus 1, that first pair of points of intersection. And then we're going to go from minus 1 to 1, the next pair, and then we'll go from 1 to 2. And that's it. That's all the areas. But for each of these, we got to figure out which function is on top, which function's on bottom, because that's how we use our area formula. Area between two curves, it's got to be top function minus bottom function. So on each of these intervals, we're going to do something like pick a test value. I think a good test value between minus 2 and minus 1 would be something like minus 3/2. And we plug it into each of our curves. So plugging it into 0, well, you just get 0 out. Plugging it into x squared minus 1 times 4 minus x squared, well, we'll have minus 3/2 squared is 9/4. 9/4 minus 1 times 4 minus 9/4. We really just need to know if this is bigger or smaller than 0, switching everything to being over quarters. So we get the first factor here is 5/4. That's positive. But the second factor here is the second factor here is 7/4. So okay, we're bigger. So positive times positive. This is the bigger function. So we'll do this minus 0. Okay, so we'll do x squared minus. I'll just quickly sort of sketch it in there. Minus 0. That'll be the setup. Okay. And again, if we go back to the picture I drew, But, again, you can do this without knowing it. You can see, oh yeah, this little quartic here, because it's a downward-facing quartic, because of the leading coefficient that's negative, you can see, yeah, it is bigger over here. I don't care what the actual value is at -3/2. The point is I know it's bigger. Just like you'll see, I'm not going to keep going back to this graph every single time, but you'll see for the next one, the x-axis will be the bigger one. So we'll do 0 minus. But let's actually justify that. Okay. So the best way to do it is to pick nice little test values. Pick a value between 1 and -1 and plug it in for x equals into each of our formulas. Now again, the y equals 0. The x-axis formula is not very interesting. But plug in a value like 0. Okay, 0 squared minus 1 times 4 minus 0 squared. You'll get -1 here. And then 4 minus 0, so 4. So -4. As I was saying, it's the smaller one. So you always do bigger function. In this case, the y equals 0. Not a very interesting formula, but still. Minus this quartic. And then on the last one, and you can already see it from the graph, this is why graphing would be so easy for a question like this. You can see it's going to be bigger, but let's go through and do the whole process. Plug x equals 3/2 into the 0 formula. You just get 0 out. Plug it into the other formula. 3/2 squared minus 1. Well, that's actually going to be 5/4 again. Times 4 minus 3/2 squared, because 3/2 squared is 9/4 again. So we get something that's positive. I don't care what exactly it is. It's 35/16. But the point is, it's positive times positive. It's positive. So again, the quartic is the bigger one. Now that we know on each of these little sort of subdomains who's the bigger function, we are now ready to finally integrate. Okay? And this is where, maybe we'll borrow some scrap paper down here, this is where we want to have our expression expanded out so that we can integrate term by term. So we'll have 4x squared minus 4, and then minus x to the 4, minus, so plus x squared. So we'll have, let's see, minus x to the 4 plus 5x squared minus 4. Okay? So that's what we're going to do. So we do that minus 0, which is irrelevant, from -2 to -1. So minus x to the 4 plus 5x squared minus 4. Then between -1 and 1, it was flipped. So you do 0 minus this thing. Well, that's the same as just changing all these signs. So x to the 4 minus 5x squared plus 4. And then we were back to the original way. This thing minus 0, so it is unchanged, going from 1 to 2. And we're just going to integrate each of these, get antiderivatives, and then that's it. We'll be all done. So the real nice thing is it's the same basic function each time. So all of these x to the 4s, we know that they go to x to the 5 over 5. This x to x squared goes to x cubed over 3. It's just a question of whether or not we're adding it or subtracting it. And then the minus 4, that goes to 4x. So we'll plug in -1 and -2. Same thing here, except now it'll be x to the 5 positive over 5, then minus 5x cubed over 3, and then plus 4x from -1 to 1. And then again at the very end, so we'll get minus x to the 5 over 5 plus 5x to the 3 over 3 minus 4x, and that'll go 2 and 1. So now we just have to evaluate each of these. It's a bit of a slog, I won't lie about that, but it's doable. We can absolutely do it. So we'll have minus, so -1 to the 5, that's just -1 over 5, so that's really positive 5. Plus 5 times -1 to the 3, that's going to be -1, so we'll get -5/3 here. And then -4 times -1 is plus 4. So we'll rewrite this, otherwise I think a lot of the little scuffs and scratches will make this unreadable for me, and perhaps certainly for you. So the first one is 1/5. So there's plugging in -1. We've got 5 more things to plug in. We'll probably have to go to the next page. We'll do minus, and now plug in -2. So you get negative of -32, so that's just regular 32 over 5. And then 5 times -8, so that'll be -40, or you could say plus -40 over 3. And then plus 8. Okay, so there we go. That's the first one. We could simplify that, but planning ahead, we're going to have a lot of over 5s. let's wait and try and group them all together. That'll probably be the best thing. What you don't want to do is right now get a common denominator of 15 on this one and then another common. Wait, try and be sort of smart when you go to simplify. So I'll do the next ones a little bit faster. So plugging 1 in, you'll get 1/5 minus 5/3 plus 4. And then minus, plugging in -1, so that'll be minus 1/5 plus 5/3, and then minus 4. And then for the last one, plugging in 2 here. So we'll get minus 32/5, and then plus 40/3, and then minus 2 times 4, so that's minus 8. I drew that one bracket a little too big there. And we got one more to go, and then it's simplify time. So now we plug in 1 everywhere and subtract, so we'll get minus 1/5 plus 5/3, and then minus 4 times 1 is 4. Okay, great. So let's take a look carefully at each of these sort of little categories. As I say, we've got a lot of over 5s. So we have 1/5 minus 32/5. So on the next page, let's get all our over 5. So we got 1 minus 32 plus another 1 minus a -1. So that's plus 1 plus another 1. So plus 1 plus 1. Okay. Plus -32. And then minus, so that's plus another 1. Okay. So that's the first bit with the 5s, or the over 5s. Now let's deal with everything that's over 3 and add it up. So we start with minus 5. Here. And then minus, so that's plus 40. Then we've got another minus 5 in the middle. And then minus another 5. Then plus another 40. And minus another 5. And we've got one more. We'll just squeeze it down here. That would be the constants. So we've got a 4 minus an 8 plus another 4 minus, so plus another 4. So 4 minus 8 plus 4 plus 4. And that'll be minus another 8 and then plus another 4. If you haven't noticed, there's a little bit of symmetry going on here. So plus a -8 and then minus a 4. So plus that final 4. Okay. So now we can start simplifying these a little bit. 1, 1, 1, 1, that's 4 minus 64. So 4 minus 64, that's going to be -60. So -60 over 5. 40 minus 5 is 30. 40 minus 5 and minus 5 is another 30, so we get 60 over 3 here. And then these two 4s and this -8 cancel out. These two 4s and this -8 cancel, so we've got 0 here. So what we're really doing is minus 60 over 5, so that's -12, and 60 over 3, that's 20. You add those up, and at long last, it's taken us quite a while, but and you'll notice, by the way, this is all just arithmetic here at the end. The integration was not that bad. But at the very end, we get an area of 8, is what's between or bounded by the x-axis and this particular quartic shape. These areas here all add up to 8.